Okay, great. So I think it's time to start. So good afternoon. It's a great pleasure for me to introduce today our last speaker of the year for the CUbit seminars, Professor Leticia Tarruell. She's coming all the way from Barcelona to visit us here and with the talk. The nice part is that she's going to be here until Wednesday, so we have time to talk to her. Before I forget, you asked me to remind you that there is going to be a slight change in schedule for next spring CUbit seminars. The speakers are again going to come Monday and Tuesday, but the talk is actually going to be moved to Tuesday 4 p.m. at this time. So with that, let me start to introducing Leticia. Well, I mean, she's one of our very diverse experimentalists in ultra-cold gases. She has done a lot of different experiments, starting when she did her PhD back in France, when she worked with Christophe Salomon on fermionic atoms studying the BC-BCS crossover. Then as a postdoc, she moved to ETH and started to work with Tillman Esslinger, trying to understand fermionic atoms, but in lattices, and she did a beautiful work on trying to explore diverse band structures, including Dirac cones and very different topological behaviors in cold gases. My understanding is she had a little bit of a short position as a CNRS, and then she moved back to ICFO, where she is a professor there, and she's doing a lot of different experiments, working with bosonic atoms, alkaliner atoms, and she's exploring beautiful physics, not from dynamical gauge fields and gauge theories to droplet physics. So she will have a chance to tell us all the exciting physics she's exploring. Well, of course, Leticia has received a lot of awards, and I just want to mention she has a ERC grant recently, and well, maybe I'm just going to let her tell us about all the exciting physics she's doing on engineering exotic superfluids with a spin orbit couple Bose-Einstein condensates. Thank you so much, Leticia.
So thank you very much, Ana Maria, for the introduction. Also, thanks very much for the invitation to come here. It has been a super interesting day, and I'm very much looking forward to the next 2 coming days to keep having nice physics discussions and see beautiful labs. So I will be telling you today about experiments that we have been doing over the last few years in my group at ICFO in Barcelona. Actually, our institute is it's located here. It's about a 20-minute drive from the center of Barcelona and very close to the Mediterranean Sea and to the beach, as you can see. So ICFO stands for the Institute of Photonic Sciences. It's an optics institute, and this is one of the reasons that motivate us to take the Bose-Einstein condensates that we investigate in my group and couple them to light, to engineer spin orbit coupling, and exploit that to engineer some more exotic superfluid phases that we are used to see with BECs. So my talk is going to be a talk about Bose-Einstein condensates. Bose-Einstein condensates that we subject to artificial gauge fields. That means to some artificial vector potential that acts on the atoms, and from which we can derive either electric fields when we take its time derivative, or magnetic fields when we take its curl. And actually, Bose-Einstein condensates subjected to artificial gauge fields have been a topic of research for really, really long time in the community. So shortly after seeing the first BECs, people set them into rotation to see vortices because they wanted to see a proof of superfluidity. And they saw these beautiful vortex lattices that actually turned out to be very similar to the vortex lattice of type 2 superconductors. And this is because there is an analogy between the Coriolis force in the rotating frame and the Lorentz force that the charged particle experiences in the magnetic field. Then there are other ways of engineering artificial magnetic fields with cold atoms, which is shaking optical lattices. And these are very nice experiments in the group of Immanuel Bloch in Munich, where you can see actually particles subjected to a strong magnetic field in a lattice. They are experiencing cyclotron orbits that have a direction that inverts when you invert the direction of the magnetic field. And what happens with these cyclotron orbits when actually they cannot close because they get close to the edge of the system? You can see here, you get skipping orbits. These are beautiful experiments also done in the group of Ian Spillman where actually the gauge fields are engineered using yet another method. This is optical coupling. So you see, these are all very nice experiments using different methods to engineer gauge fields for the atoms, but they have a point in common, which is that while the particles in the BEC are quantum, these gauge fields that are acting into them are just classical. Yeah? So they are really like a background, a classical entity that acts on the atoms. But now today I want to tell you how we can push these things a bit further and make that the quantum particles of our BEC, they just experience quantum gauge fields. So we want to make these gauge fields quantum. That means that they are going to become quantum mechanical operators that are going to act into the matter and dictate the behavior of the matter, but also the matter will act back into the gauge field that will be modified. And if you want to engineer quantum gauge fields for quantum particles, of course, you should pay attention that you take the good theory of fields. That means that you take quantum field theory. So you want to engineer gauge theories, and actually gauge theories, they are everywhere in our description of nature, because we know that gauge theories describe the interactions between elementary particles as mediated by gauge bosons, so they are really crucial in high energy physics. But if you think of gravitation, so general relativity is also a gauge theory. If you are more from the condensed matter side of things, and interested in strongly correlated states of matter, then you can see that many of the complicated strongly correlated states, like spin liquids, spin ice, they are effectively described at low energy by gauge theories. So this also helps us in our understanding of these phases. And if you are more into the quantum information side of things, then you should still care about gauge theories, because the gauge theory code is nothing else than the Z2. That is gauge theory. So the whole idea is that if we take our Bose-Einstein condensates and can make them speak this language of gauge theories, then we can do quantum simulations, so do analog quantum simulation of many, many different phenomena, more than what we could do otherwise. And that's what motivates experimentalists like me to open these quantum field theory books to try to understand what are the key ingredients that you would need to do in the lab in order to get your atoms realize these gauge theories. And then, really in a nutshell, for a naive experimentalist like me, what you need to do to make a gauge theory, and we take as example the simplest gauge theory that we are all used to, which is QED, is that actually you need matter and gauge degrees of freedom. For QED, I mean, you need electrons and photons. Then they need to be coupled in the right way. So you need minimal coupling. That means in the kinetic part of the Hamiltonian, you need to replace P by P minus A. And that's not all, because you also need to make sure that your system is gauge invariant, that the number of particles is conserved. And this is going to impose a local conservation law, such that in every point of space and time, the gauge field and the matter field are linked in this way. For QED, they are linked through Gauss' law. So in principle, if you think these two ingredients, they are not too hard to make in the lab. I mean, you could take two types of particles, and this minimal coupling, I mean, this is already what you are making for the classical gauge fields. But the difficulty comes really in this local conservation law, because this is something that does not come easily in our AMO experiments. Still, I think it's very impressive to see that over the years, AMO experiments have been progressing a lot in this direction. And at the beginning, only building blocks of these theories were made. But now we have reached out to engineer complete gauge theories. And these complete gauge theories, they are engineered in the three key AMO platforms. So with trapped ions, with Rydberg atom arrays, and with neutral atoms in optical lattices. And what is engineered in all these experiments is QED, quantum electrodynamics, in 1+1 dimensions. And here, when I say 1+1, it means actually one spatial dimension and one temporal dimension. And this is also engineered in a lattice that makes things simpler. And it's a so-called Schwinger model. But I mean, this is the simplest gauge theory that you can think of doing from this class of dynamical gauge theories to which QED belongs to. And now the big challenge in the field is to push these things forward from one dimension to higher dimensions. Yeah? But who tells you that you have to stay in page 1 of the quantum field theory books? Can't you just also engineer more complicated theories? And in my group, we thought that, well, we should move to another chapter of the Weinberg book, or also check about theories that appear in other contexts of physics. So theories that are relevant for description of many-body systems, and we got interested in these gauge theories that are so-called topological, the most famous example of which is what is called Chern-Simons theory. And now if you just, I mean, it's many pages in the book forward, you check what are the ingredients that you need to make this theory, you find that at the beginning it looks very similar, so matter and gauge degrees of freedom, minimal coupling, but it turns out that this theory has a different local conservation law. Now in this case you have magnetic field that is proportional to the matter density. So to understand a bit what this local conservation law means and what this Chern-Simons theory means, then it's good to look at the physical example. So the physical example that is described by this Chern-Simons theory is actually the fractional quantum Hall effect. So you have charged particles confined to 2 dimensions and subjected to a very strong magnetic field. And we know that this is a very interesting many-body system because this is a system where the kinetic energy is very strongly quenched. So we have very strong correlations between the particles. And for certain filling factors, we have excitations in this system that are very peculiar because when you take these excitations and you exchange them, they are not behaving like bosons or like fermions, but like something in between. They are picking up an exchange phase that is not 0 or pi, but it's any phase. So they are anyons. And it turns out that this is a complicated system to understand by itself, but you can build some effective weakly interacting description of that using the concept of flash attachment. And it's a concept that was already discussed by Wilczek in the paper where he coined this term of anyons, and actually consists in replacing these strongly interacting particles of the original system by some new weakly interacting particles, these orange ones, and to put the effect of all these strong correlations between the particles into the fact that these weakly interacting particles, they will grab a part of the external magnetic field and attach that to them. And this is what I have depicted here with these solenoids that are attached to the particles. So now if you go in the terms of these composite particles, these particles plus what is called these flux tubes, these solenoids, then the system becomes easy to explain intuitively, because you can think, for example, of this anionic phase that you get when you exchange 2 excitations here as coming from the fact that now you're exchanging 2 solenoids, so you have an Aronoff bomb phase associated to that. That's how you can get any phase. Yeah? So this is actually a theory that allows you to get some intuition on this fractional quantum Hall physics, and it has a very important quantity attached to it, which is the magnetic field that all these solenoids are creating. And this magnetic field is going to be proportional to the matter density because you see that each particle will have a solenoid attached to it in this sketch. Like the number of solenoids that you bind to a particle is going to determine which fractional quantum Hall state you are going to mimic with that. Yeah? Now, the theory that describes how these weakly interacting particles are coupling to the gauge field that gives rise to this magnetic field, so to this A, this is a gauge theory, and it's a Chern-Simons theory. And this is actually a theory that, again, looks very similar to electromagnetism. There is these particles, the gauge field, they are minimally coupled. But now it turns out that in this Chern-Simons gauge theory, the photons, it looks like they have very, 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 very large mass, such that they cannot move on their own. They can only move when they are bound to the particles, when the particles are moving. So you can think of them like photons that don't propagate anymore. They just propagate together with matter. So then you could think that because this gauge field cannot propagate without matter, then it's going to be very boring if matter is gone. But actually, this is not necessarily the case, because if you have a non-trivial topology for vacuum, then this gauge field will also have non-trivial solutions. And that's why this type of gauge theory is called topological. So now, why would we want to do that? Well, we would want to do that maybe because if you just want to get anyons in your system, for example, because you want to use these anyons for a particular task, it would be much more convenient if you get them in a system emerging from weak interactions instead of having them emerging from some very strong correlations, because that would be a simpler system to model and so on if you just want to play around with these anionic objects. And this is some goal that was identified many years ago by the condensed matter community, and there were several schemes put forward on how you could get anyons in weakly interacting systems. And then we think that in AMO systems, because we have very good control over the different blocks, maybe we can be more successful than in condensed matter to achieve that. So then the goal would be, okay, can we make this gauge theory for anyons, this Chern-Simons theory? And it turns out that this is actually pretty hard. It's hard to model, to get the 2D gauge theory, but what we can do already is to get the reduction of this Chern-Simons theory in 1+1 dimension. So this is the theory effectively for the edge of the system, and this is called the chiral BF theory. And if you think of that, it's a bit with people that want to simulate QED, and they actually, for the moment, are only able to simulate QED in 1 dimension, this Schwinger model. This chiral BF theory, it's a bit like this Schwinger model of topological gauge theory. So it's the simplest theory of this class that has the key ingredients of this class of theories. But it's actually a theory that it's interesting in its own, because you see this is a fractional quantum Hall system, so it has edge modes here, yeah? And actually in this theory they are going to show up like many body edge states, matter wave packets that can propagate in one direction, only like remaining safe bound when they propagate in one direction and not when they propagate in the opposite one, and these are called chiral solitons. So solitons that only exist when propagating in one direction. Yeah? And then this is the theory that we want to try to emulate in our lab. So maybe let me tell you a little bit more about this theory before going on. So this is the theory that you are getting when you take this 2D Chern-Simons theory that I sketch here, and you reduce it to 1 dimension. So you remove really this y coordinate, shrink this y coordinate, are only left with the edge. And this is a theory that we did not invent. It's a theory that was proposed by Silvio Rabello in the 90s as a theory for 1D anyons instead of 2D anyons, and was explored in much more detail in subsequent years by Roman Jakif and collaborators. And actually, what you do when you do this dimensional reduction is you start with this Chern-Simons theory that has a matter field and a gauge field that has 3 components, so 2 spatial components and a temporal component. And then when you do this dimensional reduction, you lose the y direction, so you will get a matter field and a gauge field with only 2 components, time and space, but then you add a scalar field that is basically proportional to this direction, this gauge field in the direction that you removed, that is called B because it's bosonic, because it comes from a gauge field that is bosonic. Yeah? And then this theory is described by the following Lagrangian. It looks very complicated, so let me guide you through it. So basically it has first 2 pure gauge field terms. So the first one is coupling this scalar field B and the electromagnetic field tensor, and it reads BF, and that's actually what is giving the name to the theory. Yeah? And then the second term is a chiral term. It's actually what is going to make that our theory is going to behave differently if particles are propagating in one direction and not in the other one. So this is crucial to reproduce the behavior of the edge of the original fractional quantum Hall system, this self-dual term that you see here, B dot B prime. And then you have here, this is much more familiar, this is just minimal coupling between matter and the gauge field. And then finally, the matter field in this example, that's how people derived it in the 90s, is bosonic, so you can have interactions between the matter particles that are polynomial in the matter density. So this is what you see here. So now when you see this Lagrangian and you're an experimentalist like me, it looks something like really complicated to do in the lab because you have 3 fields, gauge field, scalar field, matter field, and it's also Lagrangian. We like Hamiltonians, not Lagrangians. So how do you do to simulate that? So fortunately, all these fields are not independent within each other, because I said in these gauge theories, you always have these local conservation laws that are linking gauge fields and matter fields. So in this particular theory, the local conservation laws, they are linking the B boson to the matter density, and this one is maybe easier to understand. The electric field that stems from the gauge field A to the time derivative of the matter density. Yeah? So using these relations, we are going to eliminate gauge fields here, and we are going to express everything in terms of the matter density. This is actually technically called encoding in matter. It's just a complicated naming for saying that you use these local conservation laws to remove all the gauge and scalar fields and rewrite everything only in terms of the matter fields. And this is actually not a trick that we invented. I said that trapped ion experiments can do this Schwinger model. They use exactly the same trick, and it has a price to pay. So if you have these models with gauge and matter fields and you remove the gauge fields, you are left with a model that only has matter, but at the expense of having some new interactions that appear between the matter particles. And for QED, this is nothing else than Coulomb interactions. Now, if we do this trick of encoding into matter for this chiral BF theory, we are going to get some new matter fields, and they will have some new interaction term that is called chiral. This is a name that was coined by Jacques, and actually it has this form here. So this is a very weird interaction term a priori, because it links the current matter operator with the matter density. So here it's standard kinetic energy for the particles. This is standard interaction energy, but then there is this new interaction current density. And here these dots just denote a normal ordering. That means like the dagger operators on the left and the non-dagger operators on the right. Okay, so what does this chiral interaction term mean? Actually, you can look at it in the semi-classical limit, because then you can get an intuition, because if you look at the semi-classical matter wave packet, the current operator is nothing else than the velocity times the density, so h bar k over m times the density. And then if you replace that here, what you are getting is that you have an interaction term that looks like density-density term, so normal contact interactions we are used to in quantum gases, but it turns out that in front there is not a coupling constant that is constant, but now there is some coupling constant that depends on momentum. So we are going to get a system that will have interactions that will be different when we move with some momentum compared to another one. So really, if we move in one direction, we will have different strength of the interactions than if we move in another one. And this is why Jacques called this term chiral. So it's different from its mirror image. And it's a very strange interaction term we are not used to, because it has no Galilean invariance. It really explicitly depends on the velocity of the particles. So we need to make this term in the lab. And how do we do that? Actually, we use spin-orbit coupling. We use optical coupling between two internal states of a Bose-Einstein condensate that I will call spin up and spin down through my talk, or blue and green. And we join these two states through two photon Raman transitions. Now, if we go on a speed rotating frame, we can sketch like this the dispersion relation of the atoms. We have actually them displaced by 2 times the momentum imparted by the Raman lasers along this x direction, because to go from one spin state to the other one, we need to absorb a photon in one laser beam and then re-emit in the other one, and that's going to give us 2 momentum kicks. Yeah? And this is actually also, this Kr is also giving us the characteristic energy scale of this problem, which is the recoil energy associated to this momentum kick. And when we put the Raman coupling between the two, then these 2 parabolas will get coupled, so we will have an avoided crossing between them. And if we put very large omega coupling, Rabi frequency is very large, then the dispersion relation is going to look parabolic again, because omega is really very big, and we will have 2 atom photon dress states that are going to be spaced by omega. And we'll call these states plus and minus, and in all the rest of my talk, I will be focusing on this lower dress state. And you see that this looks like normal particles, parabolic dispersion relation, but there is something that is special here, which is actually this atom photon dress state has a polarization, a spin composition that depends on its momentum, because at large negative momentum, it remembers it's built up from the blue state, and at large positive momentum, it's built up from the green state. So because this dress state polarization is momentum dependent, this is called spin-orbit coupling. So this is for non-interacting particles. Okay, I did not do anything special, but if we want to get these gauge theories, what we need to do is to put interactions between the particles. And we need to put these interactions in a way that interactions between the up atoms are very different from interactions between the down atoms. And why is that? It's because if we now look at atoms in this dress state, they are just going to behave in a way that their interactions are going to depend on their spin composition. So let me explain you a bit more how this works. So if I have large negative momentum, then the atoms are essentially made up by blue atoms. Yeah, they are in a coherent superposition of blue and green, but mostly in the blue state. So they are going to scatter like the blue atoms. Yeah? But now if I go to large and positive momenta, then the interactions are going to be like those of the green atoms. So I will get G down, down. Yeah? But in the middle, I'm in a coherent superposition, so I will have interactions that go in between. And you see that to go from this limit to this limit, I will go to a region that looks approximately linear with momentum. That means that in this range of momenta here, my interactions are going to have some coupling constant that is effectively proportional to the center of mass momentum of the particles. And this approximation, this description will be valid for any momentum that is in this overall region. So I really engineer like that some effective interactions that are like contact interactions, but with a coupling constant that depends on k. And actually, the strength of this term is just going to depend on this slope, which is given by the difference of the coupling constants that I'm building up my dress states from. So this is actually exactly the interaction term that we wanted to make this gauge theory. And you see that actually we can get it in a quite simple way. So actually, this was a pretty hand-wavy explanation. We can do things in a more formal way. So we can actually write the Hamiltonian of the system restricted to the slowest band, eliminating the higher band. And then we can expand it in series, in the interaction term in series in momentum around the points that we are interested in. And when we do all this formally, then we get a quantum Hamiltonian that looks exactly like this chiral BF theory that I was showing before. So in particular, you see this chiral interaction term that comes here. So now this is all for the theory. So how do we do these things in the lab? So we do these things using potassium Bose-Einstein condensate. So in my group, we have this lab that works with potassium atoms, and potassium has two bosonic isotopes, potassium-39 and potassium-41. And these are very good atoms. For these particular experiments, we choose potassium-39 because when we go around 385 Gauss or so, then we have exactly the interactions that we like, because we are on the flank of a Feshbach resonance for this green state, the down state. So we have a scattering length that is widely tunable and it's positive. And then at the same time, the scattering length on the other state, on the blue one, is actually very, very small. So we have this very large difference of the two scattering lengths that we wanted. And then in this problem, it's not really playing a role, but we also have interactions between up and down atoms, which are also small. So that's convenient for our experiments. What do we do? So we prepare a Bose-Einstein condensate in the presence of a magnetic field that allows to tune these interactions. Then this Bose-Einstein condensate we subject to Raman coupling beams that are counter-propagating. They are going to induce this two-photon Raman transition, and we choose as wavelength for this Raman process the tune-out wavelength of potassium. This is because we maximize the Rabi frequency while minimizing the spontaneous emission, and also these Raman coupling beams, they are not making any scalar potential on the atoms. And then I told you this chiral BF theory is a 1D model, so we need to confine the atoms to evolve in one dimension. So for that, we use this optical waveguide to make sure that we are looking at 1D dynamics. And then all the images that I will be showing afterwards, they are taken in situ with a high-NA lens. So what we will do is initially we will start with atoms confined here, and then at t equals 0 we will remove any radial confinement and any longitudinal confinement here, and then let atoms evolve in this waveguide. So now if you think of this model, I told you this is a model that has these chiral interactions. So I'm going to have different interactions if the atoms are moving in one direction or in the other direction. What I need to do to probe that is to take my atoms and not leave them at rest, but kick them in one direction or in the other one, and then let them evolve in this waveguide and see what happens with them. And this is what we did here. So we started with atoms in this stress state, and we see that when we kick them to the right and let them evolve freely in this waveguide, then they are going to expand over time, while when we kick them to the left, they will just maintain their shape over time. You see they are not expanding here. There is no dispersion. No? So clearly here you are seeing that we have made a chiral system because it's a system that is different from its mirror image. The kicking right is behaving differently from the kicking left. Yeah? So these left and right propagation directions are very different. Actually, I told you the trick how we are making up these stress states is by combining these states with these very different scattering lengths. So what is happening is just when we kick to the right, we get a system that has effectively repulsive interactions, and then when we let atoms expand in this waveguide, well, they need to release this energy. That's why they are just spreading. Yeah? While when we are kicking to the left, this system has effectively attractive interactions. So the atoms are just held together by the attraction, but they are not collapsing because there is also quantum pressure. There is kinetic energy that is just making repulsion in the opposite direction. So when you combine the two effects, the attraction and the repulsion, what you are doing is that they are balancing and you are forming a bright soliton. So it's self-bound state that is held together by this balance between attractive interactions and repulsive quantum pressure. But I also told you that in this model, we are expected to have solitons, but some special solitons, these chiral solitons that can only exist when they propagate in one direction and not in the other direction. So we wanted to show that these solitons actually, they are chiral. So what we did is just make these solitons and launch them against some wall to try to see what happens when they bounce off. And this wall, of course, is not a wall. It's a repulsive laser beam that we focus on the side of our BEC. And then when we launch this soliton against it, we see that when it bounces off, it disappears. So we have a soliton that exists when we are propagating in one direction, but bouncing off the soliton just makes it expand. So it's really like a particle that exists in one direction, but it dissociates when it goes in the opposite one. And this is really these chiral solitons that were predicted for this chiral BF theory. So this, I think, is fun because this is a prediction from the 90s for this model, but it was really purely theoretical prediction of a very abstract model. But now we were able to really give reality to these chiral solitons in the lab. So I told you at the very beginning of my talk that all this story was about engineering quantum gauge fields for quantum particles, but then I did this trick of encoding all the gauge fields into matter. So I removed all my gauge fields. So that's a bit disappointing maybe, yeah, because where are my gauge fields? Can I recover them in some way? So can I observe this chiral BF gauge field in some way? So actually there is a way out, which again we learned from the trapped ion experiments, which is that you can use this local conservation law that is linking the matter density to the gauge field to just recover what was the value of this gauge field. So basically, in this case, it's really that this electric field is proportional to the time derivative of the matter density. So what we expect is that when we change the density, the system will self-generate an electric field. So it's really this back action of matter into the gauge field. We change density and an electric field appears. And experimentally, how we can do that? Well, actually, we can do that by taking our system and decreasing the density as much as we can, which experimentally for us is letting the cloud expand. So what we do is that we take the atoms in this stress state dispersion relation trapped, and now we don't kick them, we just let them there, and at t equals 0, we will remove the longitudinal trap and let them expand and see what happens. And now if we would do that with any normal BEC, it would just expand symmetrically. But here you see that when we let these stressed atoms expand, they are really expanding in a weird way because they're expanding way more in one direction than in the other one. I think this is clear from the images, but you can also see here fits to the integrated experimental density profiles, and you see really this very clear tail in this direction. So now what is happening microscopically is something very easy to understand. So we are starting with atoms which are in a superposition of up and down, and when we are letting them expand in this waveguide, then the blue atoms will move in one direction and the green atoms in the other one while remaining in the superposition. And because the green interactions are much bigger than the blue ones, then in the green side they will have much more energy to release, so they will go further than in the blue side. And that's what is going to give this skewed distribution. But of course, if I just think in terms of this coherent superposition in this dress state basis, I can interpret things in a different way. And what I can interpret is actually that what is happening is that when my density drops in the center of the cloud, I will generate an electric field that goes in one direction. And in the edges of the cloud, the density will increase because I still need to have continuity equation working, and they will just have an electric field that points in the opposite direction. And on top of that, the strength of this electric field will be different in the two sides of the cloud. So I will have a complicated distribution of electric forces that is going to distort my cloud because I will pull more here than here, and I'm pushing like this. And then this is going to give this skewed shape that we are seeing in the experiment. That means that if we actually can quantify this skewness, then we can say which was the electric field that generated that. So for that, we just need to take these images and quantify the skewness And we do that through this skewness parameter, which is just the third moment of the distribution divided by the second moment cube. And for clouds that are asymmetric to the right, with the Q to the right, this skewness parameter is going to be positive. So we can analyze actually many of these images, and you see the result here. You see the skewness, how it builds up over time, and you see really that we start with a system that essentially has no skewness, and that it increases exactly as we are expecting from the theory. So from this, we can deduce that we have this cloud that becomes asymmetric because when we change matter density, there is this self-generated electric field that is appearing. So we really have back action between the matter and the gauge field. Okay, so with this, I really want to conclude this part of my talk, where I told you how we can actually quantum simulate different class of gauge theories, this topological gauge theories. What we do actually is we simulate the simplest theory that you can think of in this class, which is this chiral BF theory that comes from reducing Chern-Simons theory to one dimension. And this theory, if you encode everything in matter, is nothing else than matter with chiral interactions that we can engineer through two-photon Raman transitions in a BEC with very unequal scattering lengths. And we were able to see the main properties of this theory, which is the existence of chiral solitons. So these matter wave packets that only exist when moving in one direction and that disappear when you invert the propagation direction, and also a self-generated electric field when we change the matter density. So now what comes next? So actually people built this chiral BF theory, not just for these chiral solitons and self-generated electric fields, but as a very simple model for one-dimensional anions, for the equivalent of anions in 1D. And in this case, of course, you cannot exchange them, yeah? But you can check their commutation relations. You will have quantum fields that have commutation relations that are not commuting or anti-commuting, but are picking up a different phase. That's how you talk of anions in 1D. And we can actually reformulate all this theory in a lattice, and we see that we are actually getting these particles with this anomalous commutation relation. So this is something that we have worked out now in theory, and the numbers are pretty optimistic, so we think we can do these things in the lab in the near future. Another thing that we have been working out in theory is to see whether besides self-generated electric fields, we could get self-generated magnetic fields. And for that, the simplest is to take this chiral BF theory, but instead of having it in a line, we can make it in a ring. And this is nice because then you can have a magnetic flux that pierces this ring, even though you are in one dimension, because otherwise you cannot take the curl of something in one dimension. Yeah? And what we see is that there will be a magnetic flux that depends on the matter density. So when you change matter density, you will have a flux that changes, and then you will have persistent currents with a value that depends on the on this flux, and this value depends on the matter density. So this we also now figure out how we can do this in the experiment. This is a theory paper we are preparing, but we also think it's realistic to try to do the measurements. And then, of course, the goal of all this would be to try to extend this approach from one dimension to two dimensions to really realize this Chern-Simons theory and get this weakly interacting theory for anions. So with this, I conclude this part of my talk where I was telling you how we can actually make these gauge fields that act on the BEC's quantum, and I really try to convince you that this is actually interesting because having these quantum fields is cool. But now, for the second part of my talk, I will remain with classical gauge fields for quantum particles, and I will also try to show you some interesting physics that arises when we have interactions of the BEC interplaying with these classical gauge fields. And the interesting physics I'm going to look at is the physics of supersolidity, and the supersolid is actually a very exotic phase of matter, a very unexpected phase of matter because it combines the properties of a superfluid that has frictionless flow with the physics of a solid that spontaneously breaks translational symmetry. So this really looks very contradictory phases, having crystalline order and flowing without any friction. And actually, they are very different phases a priori because they come from breaking different symmetries. Here, you break a U1 gauge symmetry, so when you enter in the superfluid phase, you spontaneously pick up a phase for the whole system. Here, you break translational symmetry, that's also a continuous symmetry. And a super solid, what it does is that it spontaneously breaks both symmetries at the same time. And this is an idea that was proposed at the end of the 60s, beginning of the 70s by Andreev, Lifshitz, Chester, and Leggett. And the idea that they had in mind is to take solid helium, which is the most quantum of all solids, and try to turn this solid helium into a superfluid. So the ideas are super cool. Actually, these papers, the Leggett paper, is really awesome. You can really understand how they had these thoughts. But it turns out that if you try to do it in the lab, it's very hard. And there have been many, many efforts to try to get solid helium superfluid, but nothing clear has emerged yet. So then a few years later, people had also the idea that you could start the other way around and get a superfluid crystallized spontaneously. And the idea was motivated really by liquid helium. That was the superfluid that they had at the time. Because if you look at the excitation spectrum of liquid helium, it has this very interesting structure where you have here phonons, yeah? But at a larger momentum, you have this minimum that appears, is the Roton minimum. And the idea is just that this defines a characteristic momentum scale of the system. So if you could get this Roton minimum have an energy that touches 0, the system should spontaneously crystallize, develop a crystal at a length scale that is the inverse of this momentum of the Roton. It turns out that in superfluid helium, this Roton never touches 0 energy, but this gives an idea of how you can make supersolids, which is to take other superfluids that would have this Roton type of excitations, and this you can do with Bose-Einstein condensates, because there have been many methods demonstrated over the year to engineer this Roton excitation spectrum. So you can use spin-orbit coupling, as I was telling before. You can use shaken optical lattices. This is really by engineering the dispersion relation of the atoms, but you can also use interactions, long-range interactions that can be dipolar interactions in magnetic quantum gases, or cavity-mediated interactions. Yeah? And in all these cases, you get this Roton spectrum, and the same as in helium. Well, in some cases, you cannot get to the supersolid state, but actually there are 3 systems where you can get this crystallization occur spontaneously in the superfluid, and these are BECs in crossed optical cavities that make so-called cavity supersolids. This was investigated in much detail and really pioneered by the group of Tilman Esslinger in Zurich. Then you have spin-orbit coupled Bose-Einstein condensates done both at MIT and at JQI in the Ketterle and Spielmann groups, and also dipolar quantum gases form dipolar supersolids. This is a nice image that I took from the Innsbruck group, and this has been done in Pisa, in Giovanni Modugno's group, in Innsbruck in Francesca Ferlaino's group, and in Stuttgart in Tilman Faust's group. So in all these systems, the key properties of a supersolid have been seen. So that is that you have a system that remains superfluid and has phase coherence, but that at the same time spontaneously crystallizes. However, the crystals, the properties of the crystals that come up, they have been studied in detail in cavity supersolids and in dipolar supersolids, and they turn out to be pretty different. Because in cavity supersolids, you have a crystal that is very rigid, because it actually comes from these 2 cross single mode cavities. It has a period that is fixed by the light wavelength and that cannot change. While in dipolar supersolids, they saw these crystals. You can see here actually a 3D render of how a real experimental image looks like. And they saw that this crystal is very flexible and it has a lot of excitation modes. So it's very alive, this system has phonons and so on. And then the question was, what happens with these spin-orbit coupled BECs? How is the crystal of the supersolid looking like? Is it looking like more like the cavity supersolids on the dipolar supersolids? And there were a lot of different opinions in literature. So we thought, well, I mean, we should just do an experiment and see what happens. So maybe let me explain you quickly first how supersolidity is appearing in the spin-orbit coupled Bose-Einstein condensates. So actually it comes in the same way as we did before with this 2-photon Raman coupling, but now we are going to remain in the regime of smaller Rabi frequencies, such that the dispersion relation has this funny double well structure in momentum space. Yeah? And supersolidity arises when actually, well, you focus in the lowest rest state like before, and you have atoms that occupy the two momentum wells. So why is that? Because if you go into this well, atoms are in a rest state that are mostly blue atoms, but there is a coherent admixture of green atoms. And in this right well, there are mostly green atoms, but with a bit of admixture of the blue ones. But this is happening in momentum space, but if you go in real space, everyone is located in the same place. And that means that you will have this big cloud that will interfere with the small one and the other way around here. Yeah? And then this interference of atoms with different momenta is going to give you a modulated density profile. What people like Jason Ho showed already many years ago is that this modulated density profile arises spontaneously and every time in a different location. So this is really fulfilling this requirement of spontaneous translational symmetry breaking. And also the system remains superfluid and has still phase coherence. So it really has all the ingredients of a supersolid. Yeah? So now this tells you that in principle it should be very easy to get this supersolid in the spin orbit coupled BECs. But of course here I was all the time assuming implicitly that my atoms are condensing in the two wells. But where do the atoms condense is not so obvious, because this is going to depend on the interactions of the atoms between the wells. So why is that? Because actually there will be three interactions important here. Interactions of the atoms in the left well, interactions of the atoms in the right well, and interactions of the atoms in between the two wells. And if the interaction GLR between the two wells is smaller than the interactions in each well, then of course the system will prefer to occupy the two wells. Yeah? So it will be miscible. So the two will be occupied, and then I will have my supersolid. That's where the supersolid arises. And on the contrary, if I just have very strong GLR interactions, then the system will rather prefer to put all atoms in the left well or all atoms in the right well, because that will reduce its interaction energy. And in this case, the system will become immiscible. So if I start with a mixture of the two, in some parts of the cloud, the atoms will go in one well, in some other parts on the other well. So I will not have my supersolid because this interference will not occur. So this is what you expect theoretically, and actually this is exactly what first experiments on spin orbit coupled BECs saw. So these are experiments from the group of Ian Spillman many years ago, where they really saw that if you start with a mixture with very little Raman coupling, then the atoms are in this phase mixed regime, but then suddenly at some point the system phase separated. So you are going from this miscible supersolid phase to this immiscible phase that is normally called the plane wave phase. And what seems is that the miscibility is controlled by this Raman coupling, so the interactions of these stress states are different from the interactions of the states without Raman coupling. That's why at the beginning, without Raman coupling or very weak coupling, everything is together and then it demixes. And we understand actually why this is the case, because the atoms in these wells, they are dress state atoms, so their effective interactions, as we saw before, they really depend on the Raman coupling, because when we change Raman coupling, the spin composition is changing and the interactions can change. Yeah? So you can take this system and then you can use this effective dress state interaction picture to compute the phase diagram. And what you see here is the axis that I was discussing before. So you start with a supersolid phase, and this is often called the stripe phase because the density profile has these stripes. And then as you increase omega, at some point the atoms are going to demix, what you see here. But actually there is another axis in this diagram, which is the detuning. This is because actually you can have an energy offset between these double wells. And of course, if you have an energy offset, then you will prefer also to go to the well that has the lowest energy. And that's also going to very much unfavor this stripe phase to go to the phase separated well. And then what you see when you see this phase diagram, this is a phase diagram for rubidium. That was the atom used in the JQI experiments. It's a bit scary phase diagram because here you have 10 to the minus 3. Recall that's actually like Hertz energy scale. So you're super sensitive to detuning fluctuations, to magnetic field fluctuations. But okay, you could say, well, I stabilize my magnetic field very well and that's it. But actually more worrisome is that in this axis, you actually very quickly, as you increase omega, your system will destabilize and go into the phase separated state. And this is going to tell you that you will have very little admixture of the other spin component in this well. So the interference between these two will have very small contrast, and that's going to make crystals that have very, very tiny contrast. So the prediction for rubidium is that the maximum is a bit above 4%. So it's going to be very hard to see in an experiment. Yeah? And this is actually exactly the reason why nobody studied these supersolid crystals in spin orbit coupled BECs in detail before, because they are just very hard to see, very fragile, and so on. So now what is the way out? So the way out is actually to find a system with more miscibility. So you want to have more different interactions between same spins and different spins. And one strategy that you could use, and this is what the group of Wolfgang Ketterle used many years ago, is to replace atomic spins by some pseudo-spins. These were orbitals of a double-well optical lattice, and with that they managed to get a much enlarged phase diagram, but it turned out that there were other physical limitations that really restricted still the experiments to the regime of very small spin-orbit coupling, so very small contrast of these crystals. So our strategy is actually to keep atomic spins, but choose a more favorable atomic species, and our more favorable atomic species is again potassium, but in this case we are not going to use potassium 39 as before, but potassium 41. And we choose this isotope because it has favorable scattering properties for this particular type of experiments. So if we go around 51 Gauss, we have some overlapping Feshbach resonances, and we can find a magnetic field regime where we have scattering lengths of the up-up and down-down scattering lengths that are positive and quite similar, but interactions between up and down are much smaller. And this is going to make that the system is nicely miscible. No? And then it's going, in principle, to have a much enlarged phase diagram. This is actually what you get when you do the calculation, and this is much more positive because now we want 3 orders of magnitude in this detuning axis, so much more relaxing, but more important, in this Rabi frequency axis, we actually can go to much larger Rabi frequencies before the phase separation occurs, and this is going to guarantee us a much larger contrast for the crystals, and this is the theory prediction, so we expect contrasts that are an order of magnitude larger, so more, almost 50% contrast of the modulation. And now we think this is something that we should be able to see in the experiment, and actually the experiment, it's again a BEC coupled with these Raman lasers. In this case, we put these Raman lasers forming 90 degrees, and the characteristic distance of this spatial modulation is going to be given by the inverse of the Raman momentum, which is about 540 nanometers. So now this is the system that we study, and because I started explaining this system looking at the momentum space dispersion, that's the first thing that we are going to probe in the experiment. So we start with atoms that are in these 2 rest states, these 2 minima of the dispersion, and we are going to probe their momentum distribution. And for that, what we do is that we switch off the Raman coupling and project the atoms into the bare states. And then by doing that, they acquire momenta, like these ones acquire a lot of momenta, and these ones very little. They are essentially in the same location. So if we just do time of flight expansion and we put a magnetic field gradient to do Stern-Gerlach separation, this is the type of images that we get. So we are getting 4 momentum peaks, as we expect here. And then from these 4 momentum peaks, we can do the experiment at different values of the Rabi coupling. So basically scanning the phase diagram in this direction. And we see that if we start with almost no Raman coupling, we don't see almost any admixture in these states. No? But as we increase the Raman coupling, then we have this population of these small peaks that is becoming bigger and bigger. We can actually quantify that through the spin composition, basically, of these stress straits that goes into this polarization parameter that I had before. And we can also see what is actually the momentum of the atoms in these rest states. And we see that when we have almost no Raman coupling, basically this double well dispersion has the minima in the location where the bare minima were, so this space by 2 kr. But as we are increasing the Raman coupling, they are getting closer and closer. No? And that's what we are seeing here, that these minima are getting closer. Yeah? So when you see this, you think, well, probably everything is fine because we are populating these additional momentum components, and we have this double well structure as we should. But actually, we were not satisfied by these experiments because who is telling us that everything is located in the same position in space and they are interfering, the atoms? It could be that we are seeing this, but in some parts of the cloud, atoms are all in one well, and some other parts of the cloud, atoms are all in the other well, and in momentum space, we are just making the average of everything. So we could still be seeing these 4 peaks. So if you really want to know that you have the supersolid, you need to look at this real space density modulation and really see that the density profile of your cloud is not homogeneous, but it really has this, breaking of the translational invariance. So the point is it's not so easy to do this with the spin orbit coupled BECs. It's not so easy because I told you the spacing of these stripes, these density stripes, is pretty small, and also there are many atoms in each of the stripes. So actually what in previous experiments they did to try to see these stripes was something very smart, which is Bragg scattering of light. They basically put the atoms here and shine light. And now if you have a homogeneous density profile, when you shine light into that and look at a particular angle, you will just have some Rayleigh scattering. So nothing special happening. But now if you have a modulated density profile, this will act like a Bragg grating, and then you will have this Bragg scattering spot here. And the evidence for supersolidity in spin orbit coupled BECs really came from this spot that you see here. These are the MIT results from 2017, and this is also something that was then achieved on rubidium 3 years ago. So this is good because it's telling you this density modulation exists, but of course it's pretty hard to say anything about the properties of the crystal just from this spot. So we thought, well, we need to have a different observable. And these dipolar gases, we were very jealous of them because they could really see in situ this crystal. They could see the modes of this crystal. So we thought, well, we need to find a trick to see something similar in our case. And this we did by using so-called matter wavelengthing to magnify the spatial distribution, to really like enlarge this spatial distribution to be able to see it with our imaging system. So the idea is the following. So we take atoms in this double well dispersion relation, and at t equals 0, we are going to switch off the Raman coupling and project into the burst states. And now, at the same time, we are going to put a much stronger harmonic trap along the direction of the momentum transfer of the Raman coupling beams, and let the atoms evolve there for a quarter period. And then when we do that, we will have position and momentum that will exchange their roles. That means that if we look at the density profile here, it's going to reflect the momentum distribution of the atoms. And you really see these 4 momentum peaks in this sketch that we were seeing before. And then once you have done this, then you won, because then you just need to do some standard time of flight to have the momentum go back into position. And that's what you see sketched here. And we can, by adjusting this time of flight, we can increase the magnification as we want. And we found that the good trade-off is to do about 6 times magnification, because you don't lose too much in signal to noise ratio, but you magnify enough to beat your imaging resolution. And also the density goes down a lot, which is also good. You don't have an optically dense system anymore, so you can really image. So we just prepared this sequence, and we tested it with in a lot of configurations without the Raman coupling, and we were all very excited to see what is going to happen now when we go in the regime where we think we have the supersolid, and we do this procedure. And that's why we were very happy when we got this result. And you have to think here that we start with a system that has a Hamiltonian that is translationally invariant, but still we get a density profile that is clearly spatially modulated. Yeah? Also, if you repeat the experiment many times, each time the density modulation is in a different location. And we were so excited when we saw this that maybe we did not pay so much attention to that, but actually then we wanted to see the 2 spin components, and that's why you have 2 clouds here. So we adjusted things in our matter wavelengthing sequence such that we go a little bit below this quarter period. That's going to give some small kick to the 2 momentum components, and that's pretty cool because then we can also have spin resolved images, all in one shot. So we get now direct observation of these crystals, and well, we can actually now say things about their contrast and about their spacing, and we can say whether they're like the dipolar supersolids, like the cavity supersolids, or maybe something different. So the first thing that we look at is the contrast, And we see that the contrast increases as we increase the Rabi frequency, and this is really what we expect, because as we increase the Rabi frequency, the admixture of the other spin component in the other well gets bigger and bigger, and then this interference will give us bigger contrast, so this is what we get. You also see that we don't get this almost 0.5 contrast that we were expecting in theory, but this we understand very well. It's still finite resolution, effect of interactions that blur this procedure, and so on. Yeah? But okay, you see this increase. And then the other thing that we look at is the spacing, or the period of this crystal, and we see that this crystal has a spacing that increases with the Rabi frequency, and we can see this with in situ images, and we can also actually infer that from the time of flight images, just knowing that the spacing of the crystal is going to come from the inverse of the momentum spacing. Yeah? And both things within our calibration errors are showing the same trend. You see, like increasing with omega. And why is this tri-spacing increasing with omega? It's actually because you have this double well dispersion relation, and as we increase Rabi frequency, these two minima, they are getting closer and closer, and the crystal period is the inverse of that. So this crystal period is getting larger and larger. So what we can already conclude is that people that said, well, these spin orbit coupled supersolids, they will have a period that is fixed by the light wavelength. Well, they were not right, because we see that it changes with omega, and it's really not given by the light wavelength. That would be this value here. The point is, of course, all experiments that were done, they were done just in this regime, so they could not see this increase before. So the other thing that you may wonder is whether this crystal is rigid and incompressible, like people thought, or whether it is alive, whether it can move around, whether it has phonons, excitations, and so on. So if you check papers in literature, you will find many papers that tells you that, okay, this crystal is infinitely stiff, it's incompressible, it cannot have excitations like crystals, no phonons, and so on. But actually, this is when you check mostly what you expect from the experimental point of view. This is what experimentalists think, because you really always think, okay, this is induced by light, so maybe it should be like the cavities, and the cavities show that it's in this way. But if you look at theory papers, many say something different. So there have been several studies of these excitations of the crystal, the supersolid crystal, in spin orbit coupled BECs, and they say that the crystal is compressible. And I will follow this paper here to explain you why. So you see, in momentum space, we had these 4 momentum peaks that I showed you even experimentally before. Now, what is true is that actually these 2 peaks and these 2 peaks, they are linked by the transfer from the Raman process to 2kr. So this distance is fixed. So this is like the distance between the blue and the green in the left well and the green and the blue in the right well. But of course, there is some freedom here, which is actually the relative position between these 2 big clouds. So the origin of the crystal excitations is really going to come from the relative displacement of these big clouds, or of the left well versus the right well. Why? Because actually the crystal period is coming from the interference of this big cloud with this small cloud, and the other way around. And you see that the period is going to be given by the inverse of the characteristic, the momentum spacing, and this momentum spacing is 2kr plus this relative momentum. Yeah? So that means that if this relative momentum between the right well, left well is changing, then I'm going to get crystal compression. So I will have a crystal that does like this. So we thought, well, maybe we can try to see this in experiment. And then we had a closer look at our images, and you really see here that actually they seem to be not in the same location. So we thought that actually there were all these thoughts that maybe there are no excitations in this crystal, just because, as in this paper say, everything that was measured before was in this rigid crystal configuration, but we can go to a different region. And then we thought that we should be less careful when preparing this supersolid. Instead of trying to prepare everything very adiabatically, very smoothly, let's go more brutally into this supersolid phase. So just go a bit too fast. And when we do that, we actually see a lot of excitations in our crystal. So we see global displacement of this pattern. This is just a dipole mode of your system. But we also see relative displacement of the 2 spin components. of the left well versus the right well, this is what you see here. You see what is a spin dipole mode, the two spins oscillating out of phase. No? So actually, this is going to give oscillations of the crystal period, no? Because this is really this K relative, and this goes directly on the period of the supersolid crystal. And we can even check what happens for different values of the Rabi frequency, and we see something funny, which is when we increase the Rabi frequency, even the frequency of this oscillation changes. So this frequency seems to be decreasing with omega. So actually we did last week, this is data from Friday and Saturday, measurements of the spin dipole frequency versus the strength of the Raman coupling, and you see this frequency is just going down. And actually this is where you expect for our parameters the phase transition from the supersolid here to no supersolid here. So we are fairly well following this trend. We think here we are just getting into a metastable state. So this is a first order phase transition, so you can get trapped in a metastable state. Yeah. And on top of that, we can do that at some magnetic field, which is some interaction between the different spin components, but we can also do it at a different magnetic field where the supersolid phase transition is expected to occur somewhere else, and these frequencies are expected to have different values, and it also seems to work. And these lines are really theory with no fitting parameters, so everything up to the fact that this data that is few days old seems to be agreeing with what we expect. So what we conclude from that is that clearly these supersolid crystals in the spin orbit coupled BECs, they have compression modes, and these modes are softening at the supersolid phase transition. So now our understanding is that actually this excitation spectrum is very good to find where this supersolid phase transition is, because when you're in the supersolid phase, you have many excitations, because you have excitations of the density overall, but also crystal modes. Yeah? While when you go out of the supersolid phase, you can still have excitations of the density of the BC, but you don't have crystal excitations anymore. So you have twice the modes when you're in the supersolid phase, because you broke two symmetries, than when you're out of the phase. And this is actually exactly what was seen in the dipolar system. So this is data from the Innsbruck experiment, where they could compute the things and really see that, for example, one mode branches out into two. And you also see here they have a mode that softens the phase transition. And this is actually the mode that I was showing before. It's the one with the lowest energy in this diagram. So it really seems that the spin orbit coupled supersolids are very similar to the dipolar ones, at least in the aspect of excitations of the crystal. So with this, I really come to the end of the last part of my talk. So I told you that using potassium-41 BECs, we actually can make the supersolid stripe phase in spin orbit coupled systems much more robust. And this is cool because it allows us to see for the first time not just the supersolid in momentum space, but also directly in real space using this matter wave lensing. This is only possible because our contrast is much larger, otherwise there was no hope before. We can see that the crystal spacing is really changing with Rabi frequency, so it's not fixed by the light wavelength. And also we can see that this crystal has excitations that are pointing out where is the phase transition. And now there are many things that we want to keep doing. So we want to see more things of these collective crystal modes. So we are not sure if we can see them in situ, but of course it would be cool to see the crystal just changing like this, compressing and expanding. One thing that we would like to see is an even lower energy mode than this one, that is the Goldstone mode. So the fact that if you have a crystal displacing it like this essentially costs zero energy. So we should see the stripes that slide. This is something that was seen in the dipolar supersolid, so we try to do it ourselves. And then this system has phase coherence, and it's superfluid, but it would be cool to measure the superfluid fraction. And also, all this is described by mean field theory, but we could include beyond mean field effects by going to a regime where mean field energy essentially cancel out, having attractive interactions between these two momentum wells, and we form a liquid phase that will also spontaneously break translational symmetry. So with this, I want to thank the team that did these experiments. This is the potassium spin orbit coupling team in my group, and a theory collaboration with a group of Alessio Celli at the Autonomous University in Barcelona. And maybe very quickly tell you what we do in my other lab. So this is a strontium experiment where we make strontium quantum gases. And we have this tiny glass cell with a high NA lens here, because around this experiment there is an optical lattice that we do at clock magic wavelength with 575 nanometer spacing, because this is a multi-lattice. And then we use the techniques that have been demonstrated beautifully in Twister experiments to image the atoms in this lattice. So we use imaging on the blue transition while we cool on the red transition using attractive Sisyphus cooling. And we are able to get this type of images. So we can see the single atoms in a Hubbard regime lattice. But the specificity of our experiment is that we use a different strontium isotope that all the other people. So we use strontium-84. So we can make Bose-Einstein condensates with that. And then we can load them into the lattice. And playing these matter wavelengthing tricks, we can look at the momentum distribution. And you can see here interference peaks when we look at the momentum distribution of this BEC in the lattice. And now we can also check what our system parameters. And we really can tell you that we have Bose-Hubbard superfluids in this system. So this is, I think, very exciting. So we are excited on many body physics that we can now play with the strontium quantum gas microscope. That's why the strontium team, my group, is all very smiley in this picture. And with this, I really want to finish thanking everyone in my group that worked on these experiments, and also the theory group of Alessia Celli, with which we did the theory that was behind what I presented today. And with this, I really want to thank you for your attention.
Thank you, Leticia, for the very, very beautiful talk. So we are open for questions.
Thank you very much. Can you point out why there's, as you're increasing the Raman coupling, sorry, there seems to be a bound, like the dipole, spin dipole mode doesn't want to go below 0.2.
Okay, so we are not so sure because it's too new data. So
Yeah.
you mean why
Like
it is
here,
not
yeah,
going,
in both cases,
more?
seems like it's hard to drive.
So we are not sure. At some points, the point we also have losses in this system. Yeah. So if the frequency gets really too low, we don't fit enough oscillations. So we are not really able. I mean, we need at least one full period to say something about the frequency, and this all starts to be around here. Yeah. Because what we have checked is if we don't have the Raman coupling, we don't have the dissipation, we just make a mixture, we can go to much lower frequencies than that. So I would say it's more an artifact that we don't manage to measure below, but I'm not sure. I think that this is still too early to say.
Okay, thanks.
I have two questions. One is, when you present the skew versus time, there's like, in the theory curve, there's like a reverse propagation for a while and then goes to the right direction. Is there any particular reason, or is it just from the rack of Rabi frequency?
Yes, we understand this well. This is because we start putting our lasers at zero detuning for like the single particle physics, but there is many body detuning that comes from the different interactions. So initially, first the detuning has some effective sign and then it switches. No? Okay. And that's what gives this going down and then up. No? So this, the theory predicts that. The experiment, I think it's a bit, it seems to go a bit down, but it's hard to say. I think it's in the experiment, it's really in the noise. But that's what we expect from the theory. No?
I see. So and then for the supersolid phase,
it's a bit below, but you know, it's not up here, so I think we can.
I see. It's actually still. Oh, so for the supersolid phase, how's the correlation between two different spin states? I guess for one single spin state, they form spontaneously break the symmetry, but how about the correlations between them?
So this is a very good question. So from theory, what you expect is that the stripes appear always in the same location for the two. So it's always a density stripe and it's never a spin stripe. The spin stripe costs a lot of energy. So, I mean, you can do theory and you'll never find it. Okay. So it's never like one spin like this and one spin like this. They're always together. In practice, all our data is compatible with that, but it's not so easy to really be absolutely sure because you also have within error bars and so on. No? But it really seems that they are just always together. But the location of that each time is different because what fixes the position of these stripes is the relative phase between the BECs. And each time you condense, the relative phase is something different, and then the stripes appear in a different location.
Okay, thank you.
More questions? Maybe I ask one question. So do you have an interaction that depend on your momentum? Yes, in this case. So do you think that you can have some spin squeezing? I mean, you have two states. I mean, if you prepare K and minus K or two different momentum and these have different interactions, I mean, that will generate an effective SC square term that you think that you can generate some squeezing?
So this is a good question. I don't know. I think what we have, it's the center of mass momentum. It's not the relative momentum, you know, like that appears here.
Yes, exactly. I want to have one, if you create two superpositions of different center of mass momentum, one.
Yeah, so I don't know. Yeah, I would really need to check, because I would then naively say if you create a superposition of one momentum and the other momentum, they will have different interactions, and then the superposition should be something like this. But I never did the calculation, so we would really need to check.
Any more questions? If not, let's thank Leticia for the great talk.